in today's school, we are going to study, or in other words, today's school, we are going to call it stereochemie. There's a part where we're going to diverge, okay, there's a part where we're going to start saying, okay, now we are in stereochemie, but everything we're going to do for now will be applied in stereochemie. Now, molecules or compounds, organic compounds, have got different representations. So in stereochemie, we are going to represent compounds or organic molecules in their 3D dimensions. So there's a part where we're going to represent them in the 3D dimension, there's a part where we're going to represent them in the plane dimension, etc. But for now, we are going to look at those representations that we can consider for different molecules. So the first one is what we call Représentation de CRAM. The third one, or the second one, is what we are going to call Représentation de NEWMWAN. And the last one is what we are going to call Représentation de Fischer. Représentation de Fischer. So we start with Représentation de CRAM. So Représentation de CRAM is basically the representation of organic molecules in 3 dimensions. So how do you know that this molecule is in 3 dimensions? I'm pretty sure you guys have seen organic compounds written like this here. Organic compounds written like this here, where you have a wedge. This is what you call a wedge. That black dash is a wedge. Then the dotted lines is also a wedge, but it represents something also. Then these 2 straight lines here represent the plane, So now let me explain what it is. So the 2 straight lines that you can see, the 2 straight lines that you can see here, the 2 straight lines, this one and this one, they represent the molecule in the plane, Then the wedge represents the molecule coming out of the plane, Or in other words, I'll use a page, right? The 2 straight lines here represent the molecule in the page or on the page. Then the wedge here, the dash line, the dash here, the bold dash line, represents the molecule coming outside of the page, Then the dotted lines represent the molecule behind, like something is behind. It's behind on the page. It's behind on a page. Is it clear? So the dash represents la représentation d'une liaison dans le plane de la figure. Then the 2, that is this kind of a dash or this one here, la représentation d'une liaison en avant du plane. It's in front of a plane, in front, like it's coming out of you. It's inequality. Then the last one, représentation d'une molecule arrière. Arrière is behind. It's behind in the plane. It's behind in the plane. Is it clear with these rules on what represents what on the figure? So the dotted lines represent the molecules or substituents, depending on whatever you are going to look at, that is behind in the page. Then the 2 straight lines, there will be always 2 straight lines. They represent the molecule in the plane. Then there is the last one, which is the wedge, the bold dash. It represents the liaison en avant, the one that is in front. It's facing you. Facing you. So what I'll do is this. I'll look for an image on the internet that I'm going to use to just show you guys what I mean by avant and derrière. So say is it clear before is it clear so far? Est-ce que c'est clair? Nat, is it clear?
Yes.
Just repeat the page.
Can you guys now see the page? Can you see it?
Yes.
So what I'm saying is the dash, the dash you are seeing is representing the substituent or the hydrogen atom that's behind. This is methane, methane with sp3 hybridization, bond angles that is 109.5 degrees, then with a single liaison that is sigma. So what you are seeing here is what we are calling Représentation de CRAM. Représentation de CRAM. So with CRAM's representation, we have the three. It's a 3D representation, of course. We have the wedge, which represents the substituent, or in our case, the methane molecule. The hydrogen that is facing us. This one is facing us. This one is facing us. The hydrogen that is facing us. Then there's another hydrogen that's behind. Now, because a paper can only represent 2 dimensions. A paper can only represent 2 dimensions, or a plane can only represent 2 dimensions. The hydrogen is supposed to be shown kunumauko, it's behind. Now we represent a substituent, or in our case, a hydrogen molecule, hydrogen atom with a dash, with two dashes. So the dashes here just represent that, okay, there's a hydrogen behind. Then these 2 lines here will always be in the plane. So these hydrogen atoms, this one and this one, are in the plane. They are in the plane. This is what we are trying to show. Let me just, this one here. Can you see this one? This methane molecule. Can you see it?
Yeah.
Yes.
Yeah.
So what we're trying to do is the same thing. That one is just a ball and stick model, but it's the same. So the wedge shows that it's coming out of the page. It's coming out of the page. Then the dash, or the wedge with dashes, that is a wedge with dashes. It shows that it's behind, it's en arrière, it's behind. Then the 2 are always in the plane. The 2 are always in the plane. They are always in a plane. They are always in a plane. Let me look for another example. Say ethane. Okay, so I'll start with this one first. Okay, let me start with this one. Yeah. Sorry for the network, it's a bit slow. So, can you see the screen I'm sharing for ethane? Can you see it?
Yeah.
So now this is a representation. This is a ball and stick model. It's a ball and stick model. Now, representation de CRAM, you are supposed to show with my wedge, with my dashes, but I just want to bring out the picture. I want you guys to visualize what I'm trying to say. So when we are going to represent this in the form of CRAM, representation de CRAM, we are going to have this one, this one. This one. Where is it? Is it in the plane or it is out of the plane? This one. This one. Is it in the plane or out of the plane?
In the plane.
It's in the plane. What about this one here?
The plane as well.
It's in the plane. Are you sure it's in the plane? Are you sure it's in the plane? If you can see, you can use this one here as a reference. Maybe if we start from this one. Where is it? Where is it? I see it. Please do smart. If you don't understand, please tell me so that because you'll be using this most of the times. So with that molecule that we saw that side, with that molecule
That is so.
I
don't know if I am understanding well When you say in the plane, don't you mean in the sideways?
No, when I mean no. What I mean in the plane, it means is it on a paper? On a paper, when you're doing the X or Y plane, you just put the one facing up and one facing upward and the one facing on the right or on the left. That's on the plane. You get it? You get who was asking that question?
Yeah,
Language.
it's me.
Are you doing mécanique du point?
I'm doing.
You are doing mécanique du point.
Yes.
So if you've noticed, when you're drawing the X or when you're drawing the X or Y plane, when you're drawing the X or Y plane, you always put the X and the Y on the plane, like the way the plane paper is, it's on the plane. Now, when you talk about a molecule now having the one that's arrière and the one that's avant, now you introduce the Z axis, now. If you've seen how you draw the X or Y Z axis, it's a bit different from the way you draw the X or Y. If you've noticed, have you noticed that the way you draw the X, Y and the X, Y, Z, it's different from the way you draw it? Have you noticed that?
Yeah.
You find that two planes, that is the X and the Y, they're always going to be in the plane. It depends on how you draw it, but the Z is the one that is on top. But the general one is the X and Y will always be on the plane. They will always be on the plane, X, Y, like that. X, if this is X, and this is going to be Y, or this is going to be X, this is going to be Y. They are always on the plane. Now, if you introduce another plane that is going to cut across like that, that's going to go across like that, that is now out of the plane. That one, we'll call it avant when we are that side, and we'll call it arrière when we are that side, and we're going to call it avant when we are this side because it's facing us. In other words, what is facing us is what we're calling avant. What's behind, something that we cannot see, if I use we can't see, is also something that's in the 2-dimension. Now that's something that we assume is behind. We assume is behind because on a plain paper, it's hard for us to draw a 2-dimension. You get it? On a plain paper, it's hard for us to draw a 2-dimension because it's a plane. You see, it's a plane. So the only possible planes that we can draw are the X and the Y. So when I say on the plane, I mean this one here. So if I was to use that molecule, or maybe this one, this hydrogen here you're seeing is on the plane. This hydrogen you're seeing here is on the plane. But this one here is behind, and this one is in front. It's facing you. This one is facing you. This one is facing you. Same applies to this one. Now, this one here is the one that's facing us. Steph, this one is the one that's facing us, isn't it? Isn't it? And this one here is in the plane or on the plane. This one is in the plane or on the plane. Then Iriukwe is the one behind number. It's derrière. You get it? So what's facing you? What's facing you in a molecule? What's facing you in a molecule is what we are giving a wedge. So this hydrogen you're seeing here is facing us. It's facing you, like it's facing you. Because this is just on a plain paper. Now, when you get the actual molecule, when you assemble the actual molecule, the ball and stick model, something like this. The ball and stick model, or is it something like this? When you get something, you see that okay, yeah, this molecule is this hydrogen is facing me, this hydrogen is behind, and this one is in front. You get it? Is it making any sense? Is it making any sense?
No.
It's not making sense. Okay, so
No.
so let me use this one, maybe to make sense. So can you see this sharing? Can you see it?
Yes, network is a bit slow, so it's too black. Okay, now I can see it.
And is everyone following? First of all, is everyone following? Because I don't want a situation where we explain, then someone says, oh, no, I didn't get it. It's like everyone following so far. Is everyone following so far? Is everyone following?
Yes, we're following.
Okay. So this is a 3-dimension. This is a 3-dimension of what's this? FN. 3-dimension model. So this is what you call a bow and stick model. So this is a semi-developed plane. So a semi-developed plane in 3-dimension, of course. But if it was a compact, it would have been something that is compact, of course. So I'll show you a representation of a compact one. So now, the question is, which one here? We'll start with this one. We'll start with this one. Which one is in the plane? Which one is in the plane? Between this one, and this one. Which one is in the plane? In the plane. In the plane. Is it this one? Is it this one? Or is it this one? So if I say, is it this one that's in the plane? You tell me yes or no. Is it this one that is in the plane? Okay. Now, is it this one that's in the plane?
That's what I think, yes.
Yes.
Is this one in the plane? Is this one in the plane?
Yes.
How many are saying this one is in the plane? Just raise up your hand.
This one, me, I'm following this one.
This one is in the plane.
Yes, that's what I'm thinking.
And this one is, what about this one? Is it outside of the plane or
It's REA.
it's behind it?
Behind.
No. Okay.
Yes.
I get the confusion. This one here, is it facing you or it's out of, or it's in the plane? These are two things I want you to make straight. Like you want to get these things straight. Is it facing you or it's on the plane?
I think it's on the plane, not facing me.
It's not, now which one is facing you if it's not on the plane?
I don't have anything facing me.
Ah bon? No. What I mean by facing you, it's not necessarily facing you like you're even looking at it. No. What I mean by facing you is any part of it might point at your direction, where you are. Because even this is on my PC, I'm facing the molecule. And it's automatic that this molecule, or you, the one that is seated there, this molecule is pointing at any of your body parts. This thing here, it's pointing at you in any way. Am I lying? Maybe I'm lying. This thing here is pointing at you.
No, you're not lying.
Yeah. This thing here is pointing at you in any direction. Maybe it's pointing at your hand, it's pointing at your fingers, but it's pointing at you. Tef, yo.
Yes.
No, only one person is answering. Only one person is answering. Is it clear for everyone?
Yeah.
It's clear. This is pointing at you.
Yes.
Yeah, this is pointing at you in any, maybe it's pointing at your hand. When I mean pointing at you, I don't mean pointing at your face. No. Pointing towards you, maybe your hand, your face, anywhere. It's pointing at you. Now, there is this one here, which is already definite. It's definite that this one is REA. It's behind. It's REA. We're going to denote this one with two dashes, dashes on a wedge. Now, this one is on the plane. So, in other words, what you are trying to do is, maybe this can be a shortcut that can help you. Always look for the side that is, you are supposed to look for the two sides. The two sides are the ones that are a bit confusing. The two sides are the one that is avant, the one that is facing you, and the one that's arrière. When you decipher which one is arrière and which one is avant, the one that's in the plane is never a problem. Please take note. When you decipher what is arrière and what is avant, what is in the plane does not become a problem. It's the same for me. I've done this, so for me, I can start from anywhere. It's still going to be. It's going to work out for everything, because I knew that this molecule here, this and this are in the plane. This and this are in the plane. I'll show you why I mean this and this are in the plane. Because I have done a practical where we actually look at these molecules. You look at them and you'll say, okay, this one yes is avant, this one is arrière. This is now where stereochemistry comes in. It's a third type of stereochemistry. Now, we are saying this one here is avant. It's facing us. It's facing us. So we are going to denote this with a wedge. With a wedge. What I mean wedge, that's dashed big line like that. Then this one, it will be a wedge on dotted lines. A wedge on dotted lines, like my dotted lines. Then this one is in the plane. It's in the plane or on the plane, depending on the grammar. It's going to be on a straight line, just a straight line, just a straight line, just a straight line. So we still go back to the other molecule. We still go back to the other part of the molecule. This is ethane. Now, we are saying we are supposed to look for what's avant, what's arrière, and what's in the plane or on the plane. Now, is this in the plane or it's out of the plane? This one here. Is it in the plane or out of the plane? This one.
On the plane.
Yeah? It's on the plane. Eh? Is it on the plane?
That's coming to it out of the plane.
Then
I think this is facing us.
Exactly. I like Mr. Blaze's answer. This one is facing us. What I mean by facing, please you people, when I say facing us, it's not necessarily supposed to face you like vis-a-vis. No. Facing might be the direction that it's oriented. If you were to displace, because if you were to move your phone in one direction, it's automatically going to point at you. When you move it in one direction, you move it maybe say a bit to your left, it will point at you in one way or another. But the idea is whatever is pointing out of the page, will always be on a wedge. So therefore, this one, Mr. Lengwe, this one here is out of the page. It's pointing at us. Or maybe pointing at something else, but it's pointing out of the page. It's coming out of the page. Then we have this one here. Is it on the plane or it is it's behind, on arrière? This one. Is it on the plane or on arrière? Please. Is it on arrière ou bien on the plane? This one. Talk about this.
On the plane.
It's on the plane, exactly. It's on the plane. And therefore, this one here is on arrière. It's on arrière. Now, is it clear for everyone? I show you the shortcut I used. The shortcut that I used to now decipher which one is on the plane. Then when you decipher what is on the plane, the two that are arrière and avant are very easy. Is it clear for everyone? This one here is on the plane. This one is arrière and this one is en avant. Same applies to this molecule here. This one is en avant, this one is en arrière, and this one is on the plane or in the plane. So is it clear for this part of the molecule, this part here? Is it clear on this part? This one is en avant, on the plane, and en arrière. It's behind. Is it clear? Is it clear?
Clear.
I'm saying for everyone, not just for one person. If it's not clear for you, you mention, no, it's not clear, it's not clear. We repeat. If it's repeating, if we still start back, we start back. So that I know. Is it clear for everyone? Because what I'm going to start doing next after this is something.
Oui.
It's not clear. It's not clear.
No, it's not clear.
Okay. So maybe we look for another molecule. Okay. So we look for maybe another molecule. Maybe this one. This one is a bit better. Say, it's still ethane. It's still ethane. It's a and no. Okay. They're saying it's dibromotetrafluoroethane, but still under the ethane derivatives. So we are looking for what is avant, what is to be you that's going to be answering. So we are looking for what's avant, what's arrière, and what's on the plane. Now, is this here avant, arrière, or bien on the plane? This one here, the red bow. Is it in the plane or bien on the plane? Is it avant or bien arrière? This one.
I think it's on the plane.
It's on the plane. It's on the plane, exactly. Now, this one here, is it en arrière ou bien en avant? Ou bien dans le plane?
Avant.
It's avant. It's facing us. It's facing us. It's coming out of the page. And this one is this one.
Arrière.
En arrière. Say en arrière. Now we go to the other side. To the other side. Here. This one. Is it on the plane out of the? Is it en arrière ou bien c'est en avant? This one.
Yeah, this one I'm not sure.
Okay, we'll start with okay. We'll go with this one. Where is this one? En
On the
avant.
plane.
Ah no, I'm saying this one. This one. Is it en avant on the plane or bien en arrière? This one.
This one looks avant.
Avant, voilà. And
Yeah,
this one.
it's on there.
And this one.
Arrière.
Arrière. And this one becomes what? If this is en avant, arrière, this one becomes what?
This one becomes plain.
Exactly. That's how you do it. Now, is it clear for everyone? Is it clear or we look for another molecule? I just explain more on how this comes about. So
Look for another molecule.
okay, we look for
Before
another.
we go to the next one,
Mhm.
let's just look at the previous one. I want to ask something.
Okay. So for this one, we said this one here is on the plane, and this one is en avant, and this is arrière. This one here is en avant, this here is en arrière, and this is on the plane. It's on the plane. It's on the plane. So any questions now? You can come in with your questions, sir.
I don't know how you are differentiating this other one.
How we are
this
differentiating?
other one below. Yeah, between the one
This one?
which is going up. Yeah.
And the one that
now
is
the one.
and this one.
No, just this part.
Just this one.
Yeah, this part.
Okay.
Now I don't know how you are differentiating the one which is going upward and the one which is going downward. The only difference I'm seeing is that they only have different directions.
But they're all facing us.
The orientation is the same, but the different direction in terms of going up and down.
Okay. So now this is what I'm going to ask you. Now you're saying this part is where you are a bit confused there. Which one is en avant, which one is en arrière, and which one is on the plane? Dave?
Arrière is clear. Now
avant and on the plane.
Two.
So we're saying what is avant? What is avant is something that is coming out of the page. That's coming out of the page. That's coming out of the page. Now, if the good part was that if I was to demonstrate how these things are arranged, it would have been even better because I'll be just pointing. This one is avant, this one is arrière, this one is in the plane. So this one you're seeing here, when you have the ball and stick module in your hands, when you have it in your hands and just place it like that, you find that this one here, it will always point at you. This molecule can be tilted. That is where we're going to go to now. When this molecule, like you said, the orientation is what differs, yes. What is en avant can become what is arrière. What is arrière can become en avant, depending on the tilting. We will look at that when we talk about isomers and all those things. But what is avant is what is just facing us, or maybe in our direction, or what's coming out of the page. Anything that's coming out of the page. This is a page. This is the page. This black thing you're seeing here is a page. Now, what's coming out of what can you see that's coming out of the page? Something that's coming out of the page, like it wants to come out of the page. Isn't it this one? something that looks as if it wants to come out of the page. It's coming out of the page. If I say it's facing us, it would be like maybe it's not even facing you. But something that's coming out of the page. Isn't it this one? I'm asking, Mr. Lengwe.
Nkamena.
It's this one, Tef. It's coming out of the page. Mr. Lengwe. It's this one, Tef. The one that's coming out of the page. And which one is arrière? Tef. Now, what's in the plane? What's in the plane? What I mean by in the plane, that's why I gave you an example of the 2-dimension of X or Y plane, because you do mechanic du poids, so you understand it from that aspect. So we're saying in a 2-dimension plane, on a plain paper, it's always easy because you only have 2 axes. You only have 2 axes. That's the first one, the one that's going Kumolo, the one that's going Oko in this direction. That is what you're calling the Y. And the one that's going across like that, that is what you're calling your X. Okay, this is what you're calling your Y. And this is what you're calling your X. Tef, from mechanic du point, I'm just saying X, Y, not X, Y, Z. X, Y. Now, is it clear with X, Y? Now, when you represent now the third axis that cuts across like that, when you represent an axis that's cutting across, you find that this one here is one of those axes that is coming out of the page. It's coming like that. It's one of those axes that is coming like that. Irefuma. It's coming out of the page. It's coming out of the page. Now, this one here remains on the page because it is defined by the 2 axes. That is the Y and the X. It is remaining on the page. It's defined by the 2 axes. That is the X, or the X which is below, and the Y, which is the same one as Karikurumaka. This one is on the plane also. It is on the plane also. It is still on the Y and the X plane. It's still on the Y and the X. But this one and this one, they are now in the 3-dimension. It's one that's coming out and it's facing you, or out of the page. This one is coming out of the page, and this one is also coming out of the page. This one is in, maybe not to say inside the page, but it's okay. If I say inside, maybe that's the context you might understand. When I say inside, I mean ilikunuma, because on a plain paper, you wouldn't represent something that's inside. You wouldn't represent anything that's inside. You can't represent anything on a plain paper that's inside something. You see, it's a bit hard because the plain paper is only a 2-dimension thing. You can only represent anything in 2 dimensions. Anything on 3 dimensions, you are supposed to visualize it. You're supposed to actually touch it. That's what you're supposed to do. Anything at 3 dimensions is hard to draw on a plain paper. But when you have it in your hands, you understand. Say, okay, this is where the one on a rear is. This one is one on a vo. Like there is no debate. There is no debate. Like when I was doing a TP, a practical on this, the professor will just give you the molecule, and you yourself will be like, okay, yeah, this one is on avant, this one is on arrière, and this is in the plane. Like it just comes out without even arguing, because with the 3 dimensions that you'll be given, first, that one will just definitely show you how all the things come out. But now, because we are on a plain paper, this is a plane, like this is a plain sheet. A plain sheet can only accommodate the 2 dimensions. That's the one that is on the plane and the one that is avant, the one that is facing us. The one that is arrière cannot be represented properly. It cannot be represented properly because we are going to take an aspect of, now, what is something inside the plain paper? You get like something that's inside the plain paper. Now, something that's inside of the plain paper, you can't really tell that it's inside, but you just represent it with a wedge to show that, okay, this molecule has a wedge at this point, and this substituent is at the end, or maybe it is kunuma. You get what I'm saying? So that's why I asked who's this Mutale to say, okay, you tell me which ones you feel are on avant, on arrière, and which ones are on the plane. Now she said this one here is on the plane, and you can pretty see properly when it's bien défini. It's bien défini dans le plane X, Y. It's perfectly defined on the X or Y plane. This one here and this one here, they are perfectly defined on the X or Y plane. Now, for the one that is avant, which one? This one here, and the one that's arrière, you can see that there is not a proper definition from the X or Y plane, but at least it shows us that, okay, one of them is coming out of the page and one is behind in the page. Same applies to this part here. There's one that is coming out of the page and one that's inside or arrière, kumbuyo, in the page or on the page. And therefore, this draws me to my simple analysis. Whenever you have a plane, it doesn't apply for all molecules. Please, it does not apply for all molecules. Whenever you have one molecule for hydrocarbons, one that is in the plane, always look at the one that is diagonally opposite. You look at the one that is oku, maybe if you say diagonal opposite, but you look at one that is, if it's kuntanch, if it's on top, automatically the one that is on the plane is the one that is below. It's automatic that the one that is below will be on the plane as well. But there are cases where that won't apply. There are cases where that will not apply. There are cases where that will not apply. But for this one, to just maybe give a highlight on what I mean is, whenever you have a compound or a molecule representation like this one, always look at what is in the plane. First of all, look at what is in the plane. Then you find that the one that is in the plane will show you what the other one in the plane looks like. Now, this one is on the plane, and the one that's on the plane, just by looking, you see that this one is also on the plane. This one is also on the plane. This one is also on the plane. Same applies to this one. If this one is on the plane, then it means this one also is on the plane. If this is on the plane, then this one also is on the plane. But please take note, this does not apply for all molecules. It does not apply for all molecules. Because when you look at now, because this is the first representation, we have what we're going to look at now, the NEWMWAN representation. Now, the NEWMWAN representation takes into account the orientations that Mr. Leng was talking about. The orientations that Mr. Leng was talking about. A molecule can be twisted and turned. It can be twisted. The one that was avant becomes arrière. The one that was arrière becomes on avant. The one that was in the plane maybe remains in the plane, etc. So with a NEWMWAN projection, now with the CRAM, first of all, is with a CRAM. Is it clear with a CRAM? Representation de CRAM. Is it clear? Where we have a wedge, we have the dashes, and we have the two that are in the plane. That is for a molecule like methane. But for a molecule like ethane, we only have one that is on the plane and two, that is one avant and the one that is arrière. Is it clear? So like I was saying, it's not always, please, it's not always that you can have this type of orientation where you have the one on the plane giving you direction to the one on the plane as well. It can change. It changes. What if we twist this molecule? Because, you know, these bonds are covalent bonds. They can be twisted and turned. You see, they're not like ionic bonds where you need a lot of energy for you to break them. But you can still twist them and turn them to suit what you want. So this one here can come here. This one can change, can go there. All this, they can all change. But for now, this is just maybe a highlight that can help you to decipher which one is on the plane, one that is corresponding to the other one on the plane, and the one that is on avant, and the one that is on arrière. So is it clear with representation de CRAM where you have the three? That is one on avant, one on arrière, and one in the plane or on the plane.
Yes.
For everyone. Then for everyone.
Yeah, it's making sense.
Okay.
It's
Okay.
clear.
Okay. This is the Chimie Organique manje. Also, no, 2-methyl in the Chimie Organique. So now we come to the second representation. Please follow me. Panono. Just small. If you have a question, please tell me. No, there is I don't understand. So that I explain. Because this is where exam questions come in for those nomenclature, those things that they don't ask questions on nomenclature. They ask questions on this one because they know a student will find it hard for them to know which one is avant, which one is arrière, because they all look arrière, they all look en avant, they all look derrière. So it is you now to pay particular attention to these principles that I'm going to tell you. So with CRAM, is anything the problem? Like, is there any problem with CRAM? With CRAM, Représentation de CRAM. Are there any problems with Représentation de CRAM? Are there any problems? En avant, en arrière, dans le plein. Because this one, I will do a TD, and I also give you an assignment to do at home. And this one I'm strict. Everyone has to submit, please. Everyone, you have to submit, because this one, if you don't know how to do en avant, en arrière, because the exam at the faculty, they will ask you the same questions. So it seems CRAM's perspective is okay. Now we come to the second one, which is called Représentation de NEWMWAN. The NEWMWAN. So now with Représentation de NEWMWAN, we represent molecules based on how we look at them. You see, if you've seen this card, there's like an eye here. When you look at a molecule from, I'll use this type of analogy. Amongst your students, who's amongst you guys, who's well known, like, you know the person, even if the person is working, you say, okay, this is this guy. Who's well known amongst you guys? Who's well known amongst you guys? That even if you look at him, if it's behind, you say, okay, this one is Delhi, so this one, no, this one is Ted, this one is Kennedy. Who amongst you guys? I want to use that person as an example because you always remember that person. Who? Is it Samuel?
Mukwa.
So,
Mukwa.
Okay, Mukwa. So Mukwa, we'll use Mukwa as an organic compound, in this case. So we are saying, when you look at Mukwa from the back, you will give a representation of how he looks at the back. How he looks at the back. Now, there are going to be two perspectives that we're going to look at. Now, I know some of you will be like, no, we can also look at him from the side, but for now, for this one, we're going to ignore the sides. We're only going to have two perspectives. That's the first one. You can look at him from the back and give his representation from how he looks from the back. And you just said, okay, this is Mukwa. Then there's another way you can also represent it. You can also look at him from the front, from his face, and you can also give a representation of how he looks on his face, or the whole formology, that is the morphology of his body. Now, take note. This is simple logic. Simple logic. The representation of Mukwa from the back and the representation of Mukwa from the front, are they the same? Are they the same? Simple logic. Are they the same? Oui or no? Guys,
No.
Représentation de Mukwa avant, en arrière, est-ce que c'est la même chose?
Oui.
Exactly.
No.
Alhamdulillah. It's not the same thing. That is what we call Représentation de NEWMWAN. So is it clear with this simple example? Is it clear with this simple example? Is it clear with this simple example? I'm saying, is it clear with this simple example? It's clear. It's clear. Eh? It's clear. Is it clear?
Yes.
Yes.
Alhamdulillah. So now, this is now what we're going to do.
Yes.
So please don't focus on these ones, okay? If you forget about them, these 1, 2, these ones will explain them later. Now, this is maybe just to give a bit of spice. This is where what Mr. Lengwe was talking about. So when molecules can be twisted and turned, it does not mean what is an avant remains on avant, what is arrière remains on arrière. No. When a molecule is twisted and turned, depending on what we are going to look at. If the molecule is like cyclohexene, we are going to have conformers. They are what we call conformers. Conformers are isomers formed by rotation. Now, for now, forget about all these things. I'll explain when we know what conformers. So just consider this structure, just this one. So we are saying we are looking at Mukwa from now. We're going to say we're looking at Mukwa from the back. From the back. So this will be the head and this will be the legs. Will be the legs. This will be the legs. Please always use, I beg of you, Mgaenda school, always use this example for Mukwa. It will help you. Because it will give the common sense, because it's just the common sense that you're going to be applying. So if you look at Mukwa from the back, this is the head. These are the legs. We don't know where the hands are, but these are the legs. Now, there is a carbon atom there, and there's another carbon atom there. This is what you are seeing here. This is what you're seeing here. Like, okay, I don't know how I can explain, but that's the junction. Yeah, the junction. So now, if this is the junction and this is the head and these are the legs, which you are seeing here. This is the head. This is is it what do you call this? Left or right leg? This is the left leg, and this is the right leg. Now we are looking at him from the back. We are looking at him from the back. So when you're looking at Mukwa from the back, what is on your right remains on your right, and what is on your left remains on your left, isn't it? When you look at him from the back, what is on your right remains on your right, and what is on your left remains on your left, isn't it? I want to be hearing answers, yes or no.
Justement.
Yes.
Exactly. So the head is there. This is the left leg, and this is the right leg. So now, this kaseko we are seeing here, is just to show that but there's a bond, there's a liaison. There's another carbon atom kunuma. There's another carbon atom kunuma. There's another carbon atom kunuma. Now we can't see it, as in we are looking at him in how can I put it? We are looking at him. How can I draw this? Can you see how are you looking at this thing? You're looking at it face à face, eh? You're looking at it face to face, isn't it? Isn't it?
Yeah.
That's how we're also looking at him. But because, like I said, this is on a plane, we can't really represent how we are looking at him. But this is the correct way we are looking at Mukwa is the way you are seeing this diagram. That's how we are looking at him. So the head remains in this orientation. The legs remain in this orientation, like that. They represent this orientation. Now, this kaseko you are seeing here just shows us at no kuntanjuku. There is something else also. There is something else. There is something else. This kaseko here shows that there is something else. So we know that there's a carbon atom here, which is this one here. For junction, this is just a junction. I don't know if you can call it a 3 junction, but this is the junction. So this is the head. These are the legs, the left and the right leg. Please, it's this one, not the one below. It's this one. It's this one. Then we have another one. Now we're looking at him from behind. Always take into consideration, we are looking at him from the back. We are looking at him from the back. Now, even as we are looking at him from the back, we should also look at the other person that is in front of Mukwa. While you're looking at him from the back, always also look at the person that is in front of him. Who is the second person that is famous amongst you? Is it Mukwa again? None.
Samuel.
Samuel, okay. So you have Mukwa and Samuel. They are both standing on, say, maybe 1 meter apart. But when you look at Mukwa, I don't know if they're the same height. If you look at them, you would think maybe there's only Mukwa standing there. But in the actual sense, when you come and look at him from an angle, you find that there's actually Samuel also standing there. So now, while you're looking at Mukwa, looking at his back, you'd also have an aspect of Samuel being there. You should also imagine Samuel being there, and you're looking at him also. Now, what happens is, now how are we going to represent it? We're going to say, okay, Samuel's head will be lower, even though they're the same height, even though they're the same height. Even though they're the same height, it's just a representation. We want to show that, okay, no, it's not only Mukwa that's there. Maybe say, okay, Samuel is there. Samuel is also there. Samuel is also there. But they might be of the same height. We're taking into consideration that they might be of the same height. We are looking at them. We're looking at Mukwa. We're also looking at Samuel. But when you look at Mukwa directly, you wouldn't know that there's Samuel there. But when you just go back aside, you say, okay, Samuel, and then you go back, you go back. That is why the angle here is 0, because we are looking at it at the back. We're looking at it from the back. We're not considering two angles that say, okay, let me look at if maybe let me peep and say, oh, there's someone that, no. It's at 0 degrees. So we are looking at mukwa, and what is through mukwa, we are saying, okay, kuntansh kulisamio. So, but the point quantum mechanics that no superposition, there's nothing like that. So, if this is the case, Samuel head is there, then the legs are there. What is on your right remains on your right. What is on your left remains on the left. Same applies here. So what is on your left remains on the left, which is this one. And what is on your right remains on your right. That's all. Now, what you're supposed to do is represent that, okay, the first person here that we were looking at is Mukwa, and the second person that we're looking at here is Samuel. Now, you are seeing the 2 and the 3 here. Why? Because when you're counting, like I said, when you're counting, you always count from always look for the chain principal. The chain principal in our case is, it can start from 1, 2, 3, 4. C'est la même chose, ou bien 1, 2, 3, 4. Ça reste la même, because the 2 positions that we're going to look at, that's position number 3 and position number 2. That is if you start from 1, 2, 3, 4, or it would be 1, 2, 3. Ça reste la même chose, but depending on where you are looking at it from. So this is what now you are calling a NEWMWAN projection. A NEWMWAN projection. So let me just draw, maybe to just give a vivid explanation of what I'm trying to draw. So we are saying there's this circle here, saying it's showing Mukwa's head and his legs. And there's another one here, Samuel, with the same thing. It's also showing his legs. Like that. So now, if you look at the way these molecules are drawn, they are drawn to a scale that, I don't know how I can explain this scale. There's this type of, if you've even noticed, the CH3 is on the side, then the hydrogen is like inside, like it's inside here. It's like inside. So if the hydrogen is inside, it means it also has to move, but everything has been drawn the way it looks like. The left leg is the left leg. The right leg is the right leg. The left leg is still the left leg. The right leg is still the right leg. That is what we call a NEWMWAN projection. That is what we call a NEWMWAN projection. No, this one here is just an example of how the orientation of the molecules look like. So we are saying we are always going to count. C'est la même chose. We're going to apply everything that is the nomenclature, la chaîne principale. We can count, say, 1, 2, 3, 4, ou bien 1, 2, 3, 4. Ça reste la même. Why? Because what we are looking at is this carbon atom there, and this carbon atom there at position number 2 and position number 3. When you're starting from this direction, or position number 2 prime or 3 prime. C'est la même chose. C'est la même chose. But my question is it clear with the Mukwa and Samuel representation? Is it clear with the Mukwa and Samuel representation? I am saying, is it clear with the Mukwa and, what have I done? Is it clear with the Mukwa Samuel representation? Or the Mukwa Sam projection? Exactly. What's the question, boss?
Clear.
Your network is cutting, boss.
Yeah,
Your network is cutting. So I can't get you.
You said you can't get me.
It's showering. Are you using headsets?
Yeah.
Okay. You know, it's a bumpy a bit. Okay, can you type your question?
You can get me now. All right.
Yeah.
Since we are saying that we are looking at Mukwa on an angle of 0 degrees, isn't it supposed to be like if someone is in front of him, aren't we supposed, isn't it that we won't be able to see him? So which means in this representation on the A prime, I'm failing to understand why they are showing the
two.
The two. Since we are looking at him on an angle of 0 degrees.
Okay, this is the simplest way I would answer this question. The molecule that we've been given here, how many substituents do we have? We have 2 substituents. So if I was to give you and say, please represent this molecule here, and you only represent this part, so that what you've written is not representing the whole molecule, but just representing this part. What the idea that I came up with, Moko and Samuel, was just to show you how the molecules can be looked at. Because in reality, if you're to put the molecules face à face, what Mr. Blessing is saying is true. You will never, in other words, let me use never. You will never know what the other molecule is on the other side. But because in our organic chemistry study, when you are given ethane, which is C2H, how many is it? Is it 2? That's 2 plus 2. That's going to be 6. C2H6. When you are representing it, you will never represent the first part, la face. No. You are supposed to represent all of it in its entirety. You're supposed to represent everything. Now, when you use the common sense that I said you use here on the molecules, it would mean you only represent this part. You only represent this part. But that does not justify what we are looking at. We are looking at ethene and not just this part of the molecule, you see. So we have to, now this is where we neglect the part of where we said we use a bit of common sense. Now we say, okay, what molecule is in subject? So we say, okay, the molecule in subject now is this molecule. And in representing it, we are only not supposed to represent this part, but we're supposed to represent everything that comes with it. Even though it's at 0 degrees, we are supposed to also represent what is on the other side of it. What is on the other side? Because this is a representation of like this. In other words, what you could do is you would do this. Someone might give you, this molecule and say, I want you to give me a formula brute for this molecule. Now, you just looking at this, you'll be able to say, okay, no, this is equals to this. Now, if I say this, we don't represent this here. We don't represent this. We don't represent this CH3 and the hydrogens at the end there. And I tell you, give me the formula for this one. It will only show the first part. And if I was to say the correct answer was this here, it would not be in accordance to our findings. So in other words, what I'm trying to say is, the molecule here, even though it's at 0 degrees, even if we're looking at it at 0 degrees, we are also supposed to consider what's on the other side. Because at 0 degrees, I tell you, at 0 degrees, what Bless has mentioned is very true. At 0 degrees, you are not supposed to represent the other side. But now, why are we representing the other side? We are representing the other side to complete the definition of the projection. Because the projection does not only look at what's on the face, does not look at what's on the face, but it looks at how the molecule itself can be represented in how can I put it? Yeah, in the same 0 degrees notion. In the same 0 degrees notion. Now, if we only represent one part, it means we have not justified on the other side. We have not justified on the other side. So what we are supposed to do, even though it's at 0 degrees, is represent the first face and also represent the other face. That is why, if you've noticed, there is a difference. I'll come in with these ones a bit. There is a difference between the way this molecule here has been represented, like with regards to this one here. With this one, the correct representation would have been CH3. Let me draw it to just add on to what Mr. Bless has added on. The correct representation would have been a CH3 there, hydrogen, hydrogen. Now, the correct one would have been pamene pafuta, pamene pali CH3. We also put another CH3 because it's at 0 degrees angle, isn't it? It's at 0 degrees, at an angle of 0 degrees, isn't it? That's the correct. That was supposed to be the correct representation. We're supposed to. I don't even know if I have colors here. At 0 degrees, we were supposed to represent E in papa. So we're supposed to say, okay, foot again CH3, another CH3, another hydrogen. Hydrogen, another hydrogen. But now, that is the correct common sense of applying this. That is the correct way. At 0 degrees, you are not supposed to see what's on the other side. But now, we're representing a molecule here. We're representing a molecule that is having two ends. The one that you're seeing first, and the one that you're not seeing. It's representing. You're supposed to give a representative of both, the one that you're seeing and the one that you're not seeing. Now, if you're just to put a CH3 and a put CH3, how are you going to know that there's another molecule at the end? So in other words, the CH3 that you're seeing here, maybe the shorter one, is just to show that, okay, there's something kunuma, but the proper representation would have been Pali CH3, where there's a CH3, we put another CH3 there. And where there's a hydrogen, we put another hydrogen there. At the end of the day, we would have a molecule represented just like that. CH3, hydrogen, chapo. This would have been the correct representation, just to show that at 0 degrees, you cannot see what is on the other side. But now we are just supposed to show what is on the other side on the plane. So this is why we have the CH3 that is, I don't know if you can say it's below, to just show that, okay, there is another molecule on the far end. So is it clear? The correct representation, I repeat, the correct representation in your exam, in a case where you're given an exam, is this type of representation, the conformation eclipse. But when we apply what we are saying, the 0 degrees notion de 0 degrees, it's supposed to be something like this. Why? Because at 0 degrees, it's definitely that what is on the other side, you cannot see. What's on the other side, you cannot see. But for the sake of, I don't think I call it for the sake of an exam, no. But for representations that you have molecules like this one here, you are definitely supposed to represent the molecule in its entirety, like everything that deals with the molecule is supposed to be represented on the projection. So now this comes, is it clear, Mr. Bliss? Or for everyone that had a similar question, is it clear?
Yeah, it's clear for me.
What about everyone? I said, what about everyone?
It's clear.
Okay. So we forge ahead. So this now brings us to the notion de décalé anti-shantion. So when you move these molecules at angles, so I'll use the same example, just a quick one. When who's this? Mukwa is still standing at this position, and Samuel is standing in front. Now, if you move, if someone moves a bit, maybe at an angle of 50 degrees, if Samuel moves at an angle of 50 degrees, you'll be able to see now that, okay, there was actually a person in front of Mukwa. You get it? You're able to do, no, there's actually someone that was in front of Mukwa. Then there's what you call the anti. Now the anti is a conformation anti. This is where now, say, Samuel stands on top of Mukwa. Samuel stands on top of Mukwa. Or in other words, one is looking like this. Let me draw it. If this would be possible, this example is now becoming unbecoming. In a case where you have one is there. I don't know if this can happen. Acrobatics. So one is there, and the other one is like that. The head is like that. I don't know if it can happen. Such kind of a. So this is called anti because you have an arrangement. So if this was a molecule and we're given to, if we were supposed to represent it in the anti-conformation, we would have a CH3 on top, like that, a CH3 on top, another CH3 below, with the hydrogens like that. So this is what I'm trying to say. Like, this is the anti-conformation. Anti-conformation. So don't worry, when we do conformers, I'll explain what happens to molecules at different angles. So this is what I mean by anti-conformation. Then decalé, this is just moving it a bit, just a bit. Maybe Samuel moves at an angle of 50 degrees out of the zone of 0 degrees. Yeah. So is it clear with Représentation de NEWMWAN? Okay. So where should I start from?
Where is conformation eclipse and conformation décalé?
Ah, okay. So we are saying conformation éclipsée, this is at 0 degrees. At 0 degrees, where we cannot really tell, like Mr. Bless alluded to. He said we cannot tell who is on the other side of Mukwa. We cannot tell who is on the other side of Mukwa. Now, we are saying the normal representation that would have made for this one, the normal representation that would have made from our common sense and of understanding, we would have said, okay, this was supposed to be our CH3 like that. Normally, this was supposed to be our representation like that. Like this. Because we know that at 0 degrees, you cannot see what's on the other side, which is true. At 0 degrees, you can't see what's on the other side. At 0 degrees, everything is aligned. Everything is aligned. So now, my addition to Blessing's question was, the idea is we are supposed to represent the whole molecule. We are supposed to represent the whole molecule, the whole of it, like this whole thing. Now, if we just write it like this, someone will just see that, okay, maybe there's just one carbon there, second one, and the hydrogens, chapter. You see? Is it clear, Mr. Samuel, so far? Is it clear? This is what people would think. This is just, no, there's just carbon, hydrogen, and hydrogen. That's all. But now, to just show that there's another thing, kunuma. There's another thing, kunuma. What I can do is, I can just write the CH3, punch up, CH3, punch up. The hydrogen there. Hydrogen up 40. What I'm just doing here, I'm just improvising to say, okay, no, you see, this molecule is 0 degrees. Yeah, it's hard for us to really tell where the molecule is really at 0 degrees. But the representation is that there is a molecule, kunuma. There is another molecule, there's another substituent, kunuma. Now, we are also supposed to represent it because for this representation, we are not just representing one part, but we're representing the whole molecule. We are representing the whole molecule. At the end of the day, when you give this NEWMWAN projection, if you just give someone this NEWMWAN projection, just this one, they'll be able to derive the representation de Fischer from it. They'll be able to derive representation de CRAM from it. Just this NEWMWAN projection that you're seeing here, you'll be able to derive, say, oh, no, this is a Fischer's projection. Oh no, this is a CRAM's projection. All those things. So now the idea is at 0 degrees, normally at 0 degrees with our common understanding, we wouldn't have had this CH3 here. We wouldn't have had this CH3 because we know at 0 degrees, whatever you're seeing in your direction is what is, that's all. That's the only thing you're seeing. Whatever is kunuma or in front of it, you can't pay attention to that. But the molecule is supposed to be represented d'après la projection de NEWMWAN in a way that it is going to be able to justify with other projections. Because in a case where you have been given this here, you've been given this here as your organic compound, and you've been told to say, okay, represent this on NEWMWAN's projection, or maybe let's start with represent this on CRAM's projection. On CRAM, you're going to say, okay, this one is on a Von, this one is maybe on a Rear, this one is on the plane. Same applies to this one. This one on a Von, this one is on a Rear, this one is on the plane. You are done with that one. When you come to the NEWMWAN's projection, it now becomes something that is going to be contrary to what you are going to produce. Why? Because the normal projection that we would have done, the normal one with our common sense, I say it's a common sense understanding, would have been the CH3 with 2 hydrogens. That's all, SAF. The CH3 with 2 hydrogens. Number, that does not represent this molecule. Now, for us to really represent what this molecule is and what it has, we are supposed to also include what is on the other side. We are supposed to include what is on the other side, even though it's at 0 degrees. Because the representation that we're going to give here should justify with all projections. NEWMAN's projection, Fisher's projection, CRAM's projection. It must justify all these projections. It shouldn't be a case where you have a representation in the NEWMAN that does not justify Fisher's projection, that does not justify CRAM's projection. So in other words, what I'm trying to say, the 0 degrees here, the 0 degrees here principle, where you are looking at an object and you are not able to see the other object on the other side, is a bit, let's say, it's ruled out. It is ruled out for the reason that we are supposed to represent the molecule in its entirety. We are not supposed to leave any part. We're supposed to leave. We're supposed to represent the whole molecule as a whole, the whole molecule or the whole organic compound as a whole. Now, if we leave out one of its side, when we leave out one of its side, it does not justify with the other perspective. That is the perspective, the CRAM perspective, the Fisher. So at 0 degrees, with common sense, that's what I'm saying, with common sense, with 0 degrees, you are not supposed to see what is on the other side. You are not supposed to see what is on the other side. But when you are drawing it, when you are giving it to a professor, when you're giving it to me, when you're giving it to any chemist, you are supposed to show that even though at 0 degrees, even though it's at 0 degrees, this here, the CH3, hydrogen, 2 hydrogen, there's hydrogen there and hydrogen there, is found on that molecule. It is found on that molecule. So it will be easy for me to say, okay, no, this is the molecule that this person is talking about. So is it clear, Mr. Samuel? On the 0 degrees, because the 0 degrees, I get this is where the problem is, on the 0 degrees.
Yes, it's clear now.
Then now the decalé, it's just a move. The decalé is just a simple movement. So like the molecule is just moving, maybe say 50 degrees on your right, 50 degrees on your left. Now when a molecule moves 50 degrees, or maybe let me say when Mukwa, let me use the Mukwa definition. Say if you have a person that's standing here, that is at 0 degrees, they were both at the same position. They were at the same position. And if the other one moves a bit at 0 degrees, or if someone peeps, you'll be able to tell that there's actually a person in front of Mukwa. So with other projections, that is the décalé and the conformant anti. Those ones, they are very easy to tell because you'll be able to see the molecule move. You'll be able to see the molecule move. Yeah. So is it clear with projection, the NEWMWAN? Is it clear with projection, the NEWMWAN? But is it clear with projection, the NEWMWAN?
Yes, it's clear. But on the confirmation and why the carbon atoms not represented?
Oh, no. Please. This one, that's why I said with this non-can, only look at this, only look at this. These are just examples. Where is it? Where is this diagram? This one here. chapwa. These things. No, yeah. And this one also, sorry. This one, just this one. Just these two. Just these two. They represent, yeah, they just represent this molecule. No, this one is something else. This one is something else. There's a carbon there and there's a carbon, and you only have hydrogens. So this molecule can be drawn like this. Carbon. So let me use this type of representation. This type of representation. So you have a carbon, you have carbon there. So you have your hydrogen, 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 like that. Yeah. So this one, please, this one here is represented by this, just these two. No, this one is ethane. C2H6. H6. Yeah. So is it clear with no, as in please, if we none, if okay, even though we still use it, but is it clear with projection de Newman and projection de CRAM? Is it clear with projection de Newman and projection de CRAM? Is it clear?
Yeah.
Okay, so we got the last projection. So now the last projection is what we are calling la représentation ou bien la projection de Fischer. So even those that are doing biochemistry, those that are doing biochemistry, we mentioned to say that with representation de Mr. Samuel, representation de Fischer. Now this is where representation de Fischer comes in. So, c'est une représentation pleine d'une molécule possédant un ou bien plus atomes de carbone asymétrique. We looked at this, isn't it, Mr. Samuel, in biochemistry?
Yes, we did.
So we just said the difference between la projection de Tholen and la projection de Fischer was on the carbon asymmetric. If you Mr. Samuel,
Yes.
if you
Boss, can I tweak
okay. So now here is now representation de Fischer. Representation de Fischer is just a plain representation, like H plus, just like H plus. Now the question is, what is on arrière remains on arrière? What is on avant remains on avant? What is on plane remains on plane? Now, with Fischer's projection, we are supposed to also consider what we are calling la carbon asymmetric. La carbon asymmetric. So when you're looking at these molecules, you look at them at the direction also. You're always going to look at direction. Like in the TDs we're going to do, I will show you that, okay, the molecule, like I said, when you look at Mukwa from en arrière, and you look at him from en avant, there should be different representations. Your left, in some cases, your left might become your right, and your right might become your left. You get it, eh? In some cases, your right might remain your right, and your left might remain your left. You get it, eh? You get, am I making sense? At some point, your left becomes your left, your right becomes your right. But in other cases, your right becomes your left, and your left becomes your right. Is it making sense? At some point, no, there are molecules that we are going to look at. You find that there will be that change. There will be that change. So with representation de Représentation de fiche. We are always supposed to represent it with a carbon asymmetric. Now the question that is being posed here is what is a carbon asymmetric? A carbon asymmetric is one carbon atom that has 4 different substituents. 4 different substituents. When you look at this here, this molecule here, it has got 4 different substituents. We have this one here that can stand in for aldehyde. You have here the hydroxyl. You also have this one here that can be a secondary or a primary alcohol. And you also have this one here, the hydrogen atom. There are 4 different substituents. An example that can be hydrogen, chlorine, fluorine, bromide. These are 4 different substituents. And I said, for those that are taking biochemie, a carbon that is asymmetric will always be represented by an asterisk, which is a star. You'll be representing this carbon here with a star because it is asymmetric. It has got 4 different substituents. 4 different substituents. So this is where Fisher's projection is based on. So Fisher's projection is based on la principle de la stereo center. It is based on the principle of the carbon asymmetric, which is also called the stereo center. It's called the stereo center. So in our case, please, in our case, c'est la même chose. You know, these representations look a bit tricky, but it's the same thing. En avant, en arrière, en plein. C'est la même chose. If you look at this molecule, now, there are 2 perspectives. Please, I said the 2 perspectives that we're going to look at is looking at a molecule in front and looking at it from the back. In front and the back. No, never the sides, eh? Never the sides. Because in the sides, you have total disaster representation. But it's in front and behind. So we're looking at them, you're looking at them at different angles, of course. We're looking at them at different angles. So here's a molecule that we have here. Here is a molecule or example that we have. Now, looking at it from this side, looking at it from this side. So your left and right remain your left and right. These are like your arms. These remain like your arms. Your left and right. These are like your arms. These are like your arms. The left and right. So this is on your left, of course, and this is also on your right. This one here. You're looking at it, but you're looking at it. It's on your left and it's on your right. It's on your left and it's on your right. Now, whatever is on the plane, remains on the plane. Whatever is on the plane remains on the plane. So with Fisher's projection, it can be represented like the way you're seeing here with my wedges, and with my dash wedges here, with my dash wedges, Now, for molecules like this one here, the Fisher's projection changes a bit. It's the same as this one. Why you have to my wedges and all those things. But now the Fisher projection that you guys are going to be using at all times, the Fisher projection that you are going to be using at all times is in the form of a plus, like this one you're seeing here. Other than writing the wedges and the dash wedges, you'll be using this representation here, which is a plus representation. So take, for instance, you have this hydrocarbon organic compound, and you've been taught to represent it. Now you're looking at it. Now this is where I said perspective matters. Someone is looking at it from this side, and the other one is looking at it from this side. So we have 2 representations that are different. So the first one will be the CH3 still maintains its position. It maintains its position. It's still on the plane. So like I said, whatever is on the plane still remains the plane. Whatever is on the plane remains on the plane, which we have here. This is the plane here. We have this plane. We have a CHO and we have a CH2O. They are still on the plane. They are still on the plane. This CHO, CH2O, H. They are still on the plane. They are still on the plane. Then you're looking at it from this side. You are looking at it from this side. What is on your right remains on your right. The hydroxyl is on your right. And what is on your left remains on your left. And which is our case. What is on our right remains on our right. And what is on our left remains on our left. What is on our left remains on our left. What is on our right remains on our right. Now we take the other side. You're looking at it from this perspective. You change and look at it from the other side. Now, when you look at it from the other side, it's actually like, how can I call it? I'll call it, okay, for now, I'll just create a mirror image of this one. I'll call it a mirror image because when you put a mirror here, this one will be on the, it will to be kunuma, shanshan, all those things. So the one on a plane will always be on the plane. It will always be on the plane. Always be on a plane. It's always going to be. When I mean on the plane, it's like a straight line, like moving from top to bottom, like from A to B. That's what I mean by it will always be on the plane, like from A to B. Then your C and D might vary depending on how you are looking at it. So in our case, we still have the arrière avant. So what is on your left is hydroxyl, and what is on your right is the hydrogen. What is on your left is the hydroxyl, and what is on your right is your hydrogen. When you're looking at it from this side, when you're looking at it from this side, maybe let me do this. Let me do this. This is your head, and these are your arms. This is your left, and this is your right. Same applies to this one here. This is your right, and that one there is your left. So this is what I'm talking about. So the positions also will vary depending on molecules, because when you talk about isomers, we have principles of changing directions and removing of bonds and creating of new ones, etc. Yeah, but basically Fisher's projection takes into account the carbon asymmetric, which is a carbon atom that is bonded to 4 different substituents. 4 different substituents. 4 different substituents. If a carbon atom is bonded to, if it was in this case, if it was in this case, you have A, B, A, C. This carbon here is not asymmetric. Why? Because it has got 2 identical substituents. It has got 2 identical substituents. Then you can also have molecules that have this type of arrangement: A, B, A, B. So these molecules are, they do not have also a carbon that is asymmetric because they have identical substituents. They have identical substituents on both ends. This there, and that one on the other end. So is it clear with Fisher's projection? Fisher's projection takes into account the carbons that are asymmetric. And this is where we build the difference between Fisher's projection and la representation de Tollen. For those that are doing biochemistry, this is where the difference comes in, where one is represented with a carbon that is asymmetric and the other one is not represented with a carbon that is asymmetric. But with Fisher's projection, it's the same thing. It's just a derivative of la projection de CRAM. If you've noticed, c'est la même chose avec la projection de CRAM, but now you just use these rules here, which are the one that is in the plane will have the chain that is going to move from top to bottom. That is this type of orientation, that is A to B. The one that is, I wouldn't say the one that is on your, the one that was on your right remains on your right, and the one that's on your left remains on your left, depending on which direction you're looking at it from. If you're looking at it from this angle, this is going to be a hydroxyl on your right and the hydrogen on your left. When you're looking at it from the other angle, it will be hydrogen on your left, or on your right, sorry, and the hydroxyl on your left. So far, with the three representations: Représentation de CRAM, Représentation de Fischer, and Représentation de NEWMWAN. Are there any questions? Are there any questions? Are there any questions?
No. No.
Is it Kushimzien? Kushimzien. Kushi. Kulshi. All is well. Eh? I'm asking.
Yes.
Everything is okay. Guys, mambo kopya organic chemistry, mambo yofya. So this is an example of NEWMWAN's projection. So the next TD we're going to have will be moving from CRAM to NEWMWAN and Fischer. CRAM, NEWMWAN, Fischer. No, perspective. Perspective is this type of representation. This type of representation. Perspective is just like semi-developed plane, shan, all those things. Now, to just wrap up, so at next time when we come, we start doing organic chemistry, man. Okay. So for now, I'll be just explaining things. I'll be just explaining, because the next part we're going to do, these parts are just notes, so there's nothing much involved. So we are done with the projection. So la compétence acquise à l'issue de ce chapitre, vous devenez maîtriser comment procéder pour écrire une molécule avec les différentes représentations. That's all. What you're supposed to do? Peut-être ou bien être capable de passer d'une de ces représentations à une autre. So in the next TD, we are going to, I'll give maybe 3 molecules. I'll give 3 molecules. Then we're going to give each representation. We're going to look at it from the left. We're going, oh, not left, sorry. We're going to look at it from avant en arrière. That is for 3 molecules. It would mean for 3 molecules, we're going to have 6 representations. For 1, there are 2 avant en arrière. So it means each molecule have at least 6 representations. 6 representations. 6. I'm pretty sure at the end of that, cool. That's a TD. Kushi Muzien. Kushi Muzien. But as we go on, I'll still give exercises so that you practice on a representation de CRAM, NEWMWAN, and Fischer. Yeah. So if there are no questions on those representations, alhamdulillah. If there are no questions, alhamdulillah. So I just wrap up with a few explanations on isomers, and on the other day we finish organic chemistry. So an isomer, first of all, what is an isomer? What's an isomer? Guys, this is not new data. What's an isomer? What's an isomer? What's an isomer?
Isomers are compounds having the same molecular formula but different structure formulas.
Voila. So an isomer is an organic compound that has the same molecular formula, that is the formule brute, ou bien la formule semi-développée est différent de la formule brute. So an isomer is an organic compound that has the same chemical formula. The chemical formula is where you have the C2, all those things, but has a different structure formula. It has a different structure formula. So in other books, the ones that you guys will be doing, they will be saying formule brute. A formule brute, which you are saying here, par définition, les isomères sont des espaces chimiques qui ont la même formule brute. Même formule brute should also mean the same empirical formula, can also mean the same chemical formula. C'est la même chose. Mais l'écriture est différente par l'arrangement des atomes, groupe d'atomes dans le plane, écriture de plane, ou bien dans l'espace à 3 dimensions. Space à 3 dimensions. Now, when we include l'espace 3 dimensions, we now come up with a new notion. Now, the notion that we come up with is what we are going to call stereo-isoméries. Stéréo-Isoméries. Stéréo-Isoméries. That's the new notion we're going to come up with. Stéréo-Isoméries. Now, isomers can be classed in three families. There's what we call isomère ou bien isomérie de fonction. Oh, sorry, isomérie de constitution, isomérie de conformation, isomérie de configuration. There are three. There's isomérie de constitution, isomérie de conformation, isomérie de configuration. So now, the most tricky part amongst all these is isomérie de configuration. But ça va aller, on va le faire. Configuration, this is now where we have molecules being moved, like you have the breaking of bonds to form new ones so that you have isomers and all those things. But with isomérie de configuration, you have the twisting and turning of molecules. You have conformation, bâton, conformation, chaise, conformation, envelope, etc. Just moving bonds. Then constitution. Constitution is what you guys have learned from grade 10 to grade 12. Grade 10 to grade 12, you've been learning isomérie de constitution, where you have la chaîne qui est différente, la chaîne ou bien la squelette qui est différent, like this one here. So N-butène, c'est la même chose avec 2-méthylpropène, c'est same thing. Même formule brute, mais la structure ou bien la chaîne principale différente. Then you have isomère de position. So you have those ones like this one here. You have but 1 in and you have but 2 in. They are isomères de position. So the position of the liaison here is what differs. So you have one at what's this? At number 1 and the other one at number 2. Then the last one, which is isomer, for alcohols also, you have maybe it's position at number 1 and position number 2. So like I said, the nomenclature for alcohol is very easy. You just have to put in the hydroxyl. But the chain principal, all those principles that we've done, c'est la même chose. Nothing changes. It's the same principle. Then the last part will be isomérie de fonction. So we have molecules that have got the same molecular, that is formule brute, la même formule brute, mais la structure différente. You have ethanol, which is different from methoxymethane. So this is ethanol, and this is methoxy. So this is an ether, and this is an alcohol. So this is why we're saying différent de fonction. Functions can be aldehydes, can be nitrites, can be cetones, can be thiols, amines, alkenes, etc. Those are functions. So you have molecules that have got the same formula brute, but they have different structures. When you look at them in detail, they have different structures. Then other examples would be acid butanoic, then butane 2,1,4-diol, and hydroxyl butanol. So this one here is an aldehyde. This one here is an alcohol with 2 hydroxyl functions and possesses a double liaison. And the other one here is a carboxylic acid. But they are formule brute. Attention, they are formule brute. A formule brute is something like this, an empirical formula. Their formule brute is the same. So it says here, les trois composés différents par la nature et la fonction, elles ont la même formule brute, which is C4H8O2. Ce sont les isomères de fonction. So what differs, or what makes the change or the difference between these isomers is just the functions. This one here has a carboxylic function, and this one here has 2 alcohol functions, and we call it a diol. Then we have one that has a hydroxyl and an aldehyde function, which is carbonyl. So this is where we have the 3 different isomers found in the isomérie de constitution. So isomérie de constitution is where you have the difference in the function, the difference in the position, and the difference in the enchaînement, like the way the chain is. So that is to do with isomérie de constitution. Are there any questions? Okay, so now, isomérie de configuration. Isomérie de configuration. Deux isomères de configuration sont des stéréo-isomères non conformés, c'est-à-dire pour passer l'une à l'autre, il faut au moins briser une liaison covalente. So the idea here is for you to form another liaison, there is always need for us to break one liaison to form another liaison. You get it? For us to form a liaison that is a covalent bond, we are supposed to break one and make the other. So you say, autrement dit, si deux structures isomères ne sont pas stéréo-isomères de conformation, alors ils ont des isomères de configuration. If they're not isomers, that is conformation, it means they are isomères de configuration. Because an isomère de conformation, you have the bond, you have, how can I explain? Bonds can be twisted and turned. You cannot break them, but you can just twist them and turn them. You can twist them and turn them. There is no steric hindrance there. But now, when you come to explain about stéréo-isomère de configuration, there is need for us to break a liaison. There is need for us to break a liaison for us to make another liaison. I hope it's making sense. For isomère de conformation, you can just twist and turn molecules. There is no need for us to break bonds to form new ones. No. With isomère de conformation. Now, isomère de configuration, there is need for us to break a bond and make another one. Alors, pour conclure, deux stéréo-isomères de configuration sont deux molécules différentes qui on peut séparer car elles ont des propriétés physio-chimiques différentes. Therefore, when you have two isomers that are formed from the separation of two or more bonds, they differ in the way they interact with nature. That is in the physical way or in the chemical way. So therefore, their properties also differ. Some isomers have similar properties, some don't have the same properties. This is because of such factors of bond breaking and bond formation. Yeah. So I think for now, for now, we call it a day. So for those doing what is it called? This module called